Hey class, it's Mr. Hofstad here with lesson 4 of our last unit, unit 6. We've been talking about SHM, or simple harmonic motion, so far in this unit, and we're going to continue to do that today. And we're going to make a new connection of something that we've been looking at for a large part of the year, pendulums. We've looked at these in terms of dynamics and forces. We've looked at these in terms of energy. Now we're going to look at them and see how they actually kind of represent simple harmonic motion on their own, as long as they're less than 15 degrees. So the angle of deflection, which is the angle between our equilibrium position and the max swing of our pendulum, has to be less than 15 degrees. As soon as it starts swinging out more than that, we no longer have a nice sinusoidal graph because of some little more complicated math that we're not going to get into about small angle approximations. But essentially, if you start going up too high, we're getting a graph that no longer is perfectly sinusoidal and therefore no longer can be classified as simple harmonic motion. But as long as we have a small angle here and our pendulum is just swinging back and forth with less than 15 degrees, or that would be 30 degrees total, then we can classify this and analyze it as simple harmonic motion. So when we're doing that, we have this new formula, which is also shown on our formula sheet as the T, or capital T, which is period, is equal to 2 pi times the square root of L, the length, divided by gravity. So we already know what period is. We already know gravity's constant. 2 pi is again just related to the arc length that we're traveling because it's following a circular path. That's where we're getting in our 2 pi. Having to do with radians, and you math buffs will be able to derive this from our circumference formula. And L is our new variable here that we haven't looked at yet in this unit. It's just the length from the axis to the center of mass. So that point about being the center of mass is important. So the center of mass isn't going to be the very end of it, it's going to be the middle of it. And they'll often give us examples that actually tell us the center of mass. Sometimes we'll have to calculate that on our own, but not very often. All right, so we aren't in the classroom, so this first example is going to look a little different. I don't even have a pendulum set up. I'm just going to give you the information here. So we're going to say that we have a pendulum, looks like this in the classroom. I'm going to let it go, make sure that it has a small angle, and imagine this in your mind. It's going back and forth, and it does 15 cycles, right, there and back, in 32.7 seconds. So let's go through this. All right, here's our first example of lesson 4. We have our pendulum, imaginary pendulum in the classroom. It's swinging back and forth, less than 15 degrees of deflection. And it takes a whopping 32.7 seconds. And we're doing 15 cycles. So our first step in order to use our period formula, we're going to find the length of this pendulum to the center of mass without using a ruler or measuring tape or anything. We can actually do it using this pendulum simple harmonic motion formula, which will only work for angles less than 15 degrees. So we're looking for our length. First, we need to calculate our period. So period is always going to be how many seconds per cycle, whereas frequency is how many cycles per second. Right? Hertz would be 1/seconds, whereas period is seconds per cycle. So to calculate our period, we need time on top because we're seconds per cycle. Time total divided by our number of cycles. So the total time we let this thing swing in our imaginary classroom, because we're not allowed in there right now, is 32.7 seconds, and it's doing 15 cycles. So we're going to divide 32.7 by 15 and we get 2.18 seconds, and that's going to be per cycle, which is our period. 2.18 is our period, capital T. Now let's do some algebra, and it's very similar to our last couple lessons where we have a square root that we need to take care of first so that we can solve for the length. So in order to get rid of the square root, we're going to square everything on both sides. In doing that, we get t squared is equal to 4 pi squared. That's going to be something that we're going to forget occasionally, and it's going to give us the wrong answer. So do your best to remember this square is applied to everything on this side. 2 squared pi squared becomes 4 pi squared. And our square root is being canceled out by the square, and we're left with this. Now, still looking for our length, we're going to multiply both sides by gravity g and divide both sides by 4 pi squared. And you'll see everything cancels out except for length, and we're left with length by itself. And on the other side we have period squared times gravity's constant divided by 4 pi squared. And we can put in all of the information we now know. 2.18 seconds per cycle is our period. Remember to square it. Gravity. In our classroom, we are on Earth, so we will use 9.81 meters per second squared. That g is not being squared though, because it was in our square root. And we're going to divide it by 4 pi squared. When we throw that in our calculator, we get a length of our pendulum of 1.18 meters. Don't even need a ruler, and we can figure out that pendulum length. Alright, let's check out our next little bit of pendulums. So that was our period. Let's look at the energy of a pendulum, which we've done before, but now let's bring in simple harmonic motion to it. So we want to use the conservation of energy like we did in Unit 4 to analyze this pendulum. When it's at its highest point, it's at rest, so we have 0 kinetic energy and maximum potential gravitational. And that's going to be the same at either end of our pendulum swing when it's at its highest point. And when it's at the center is when it's traveling fastest, so it's maximum EK, and it has no height, therefore no potential gravitational energy. Now, we know that its conservation of energy states that the potential gravitational energy here or here at max height is equal to the kinetic energy at the bottom. So let's look at a different planet for this example. We have a different planet on which a pendulum of length 2.7 meters. So that would be to the center of the mass of the pendulum. That's our length. Length is 2.7 meters. And we know that it's oscillating, it's swinging back and forth, so that it does 16 cycles in 42 seconds. Let's right away, like we did last time, find the period, which is the total time divided by the number of cycles. Here the question tells us the total time is 42 seconds, and the number of cycles it does in those 42 seconds is 16. So we get 2.65 seconds per cycle. Right, period is just in seconds, so I'll leave it like that for this one. If the bob's maximum height is 130 or 1.3 meters at either end from our reference point, we want to determine the maximum speed. So we're going to need to use energy to do this. So we know length, we know period. We actually need to know something different because we are on an unknown planet. We need to find gravity constant on this planet. So let's take a look at our newfound equation. Period is 2 pi square root of length over g. We're trying to solve for gravity's constant on this new planet. Again, like our last example, we're going to need to square both sides, which lends to the same starting point. Sorry, 2 squared becomes 4 pi squared L over g. We want g by itself, so I'm going to bring it over to the other side by multiplying both sides by g and dividing by period squared to get it by itself. Now I have my gravity constant is equal to 4 pi squared L length over period squared. I will throw in my values. 4 pi squared length was 2.7 meters, and my period in seconds was 2.65 seconds squared. We could take a look at the units right here. Gravity, this is acceleration due to gravity, or the gravitational field strength, should be in meters per second squared, and it is. And it gives us 15.47 meters per second squared. All right, now we have gravity's constant. We can do our conservation of energy. So this would be our principle of physics 5. It's always important to keep track of these principles of physics and know where to find them on the back side of our formula sheet. Certain questions, especially in physics 30, will be very targeted at those principles of physics and knowing how to state them. So using conservation of energy, we know that the total mechanical energy, right, if we say total energy, it's at this point equivalent to mechanical energy at the start is equal to the total energy at the end, our final. So we have our reference height at the bottom. So it has 0 height when it's at the bottom of the swing. That's when we have EK max. And we know that our total gravitational potential energy at the top is equal to our max kinetic at the bottom. And those are both energies. They should both be in joules. So our m, gravity's constant, which is 15.47, times our height at the max at the top, which was 130 centimeters or 1.3 meters, is equal to half our mass times our maximum speed at the bottom squared. Because at the top it has no kinetic, at the bottom it has no gravitational potential. Right? It's all potential, it's all kinetic, like we stated here. So the question wants us to determine the speed. So we're going to right away realize that the mass isn't important, which is good because they don't tell us the mass. Right? They'll cancel out if we divide both sides by mass. Next, we're trying to solve for this v, so I'm going to multiply both sides by 2. And I get v max squared is 2gh max. And I could just take the square root of both of those. And I get v max, which I'm looking for, is equal to the square root of 2 times gravity's constant times that maximum height of the pendulum. And I'll put in my values, 15.47, which we calculated first off in this question, or second after period. And maximum height was 1.3 meters. And that speed at the bottom of the swing is equal to 6.3 meters per second. And we had to do a whole bunch of stuff to get to that because we are on a different planet and didn't know gravity. All right. Is that all for today? That is. Good luck with your homework. Please let me know if you have any questions with any of these remaining lessons. We're getting down to the wire here. Hoping you guys are doing okay with this stuff, but I don't know unless you let me know. So stay in touch, keep connected, and we are so close to being done. Good luck, everybody.